Structure. We see it everywhere we look in the universe. From the elegant tendrils of spiral galaxies to the regular orbits of planets around a star like our own, to the DNA that carries the code of life. We see again and again that nature creates larger structures from collections of just a few smaller types of components, and this creates tremendous variation. Billions of stars are organized to make galaxies. Any number of planets and stars come together to form solar systems, and so on. If we continue to shrink our scale, we see that nature continues her trend of using modular constructs of just a few simpler structures to create a truly awesome and diverse universe. In this lecture, we're going to discuss one of the smallest systems that follows this tenet. Indeed, one of the smallest systems in all of creation, the atom. It's important to start our discussion by pointing something out. Atoms actually can be divided, but doing so causes something very special to happen that doesn't happen when we divide larger samples of elements. Take the example of a bar of gold. That bar of gold can be cut in half to make two smaller bars of gold. Those can be cut into smaller pieces as well, and they're still gold. And the process can continue, creating ever smaller and smaller samples of that element, gold. But if we could continue to do this perpetually, eventually we would arrive at a point where we have just one atom of gold left in our sample. So what now? Is that atom of gold truly indivisible? Actually, no. It can be divided, but in doing so, its identity changes. The two fractions created by splitting an atom of gold are no longer gold. They're something else. But this leads us to an interesting question. What are atoms themselves made of? If they can be split into other smaller atoms, then they must be made of even smaller pieces of matter than atoms themselves. And in fact, they are. Atoms are comprised of just three types of particles called subatomic particles: positively charged protons, negatively charged electrons, and neutrons, which have no charge at all. Protons and neutrons are of nearly equal mass and reside in a dense nucleus at the center of the atom. But much smaller negatively charged electrons orbit that nucleus, balancing out the positive charge that's provided by the protons. Most of us are familiar with this depiction of the atom, but the story of how we came to understand it is every bit as fascinating as the structure's own elegance. So today, we're going to try to understand how each of these particles was discovered and how generations of scientific work ultimately came together to create our understanding of the most fundamental unit of matter, the atom. The notion of atoms was first forwarded by ancient Greek philosophers who postulated that there are just a handful of fundamental substances. Now, they combine in various ways to form all other substances. The Greeks widely believed these elements to be air, water, earth, and fire. And they also believed that particles of these elements were absolutely indivisible. Of course, today we know that none of these things are actually elements. And we also know that atoms of true elements can in fact be divided, just that they change into something new when they are. Nonetheless, the Greek term atom, literally meaning not divisible, has stuck and is still how we refer to the smallest quantity of a given element that can still exist as that element. Western discourse over the nature of matter and its fundamental units slowed to nearly a halt with the fall of ancient Greece. And it wasn't until the start of the 19th century that the concept of the atom was revived, primarily as a result of the work of John Dalton. Dalton didn't have the sophisticated scientific instruments that we do today, so he had no way to see or experiment directly on atoms. What he did have, though, was a keen intellect and the benefit of the work of Lavoisier and others. Using relatively simple observations, Dalton was able to formulate a sound atomic theory based on his observation. Let's begin by considering a couple of reactions that Dalton himself may have been able to run and observe himself. Here's a molecule of oxygen. And we're going to react that oxygen with 2 molecules of hydrogen. Now, when I do this, I create water. This is a relatively simple reaction and one that he could have run himself. Similarly, we can react oxygen with hydrogen, but instead have 1 oxygen react with 1 hydrogen molecule. And in this case, we create a different compound known as hydrogen peroxide. Now, Dalton could have made both of these, and he could have determined the masses of his starting materials and his products. So let's say that he does this. And he was able to determine that when 32 grams of oxygen react with 4 grams of hydrogen, 36 grams of water are produced. This is known as the law of conservation of mass, because 32 plus 4 equals 36. And he could similarly observe this when he made peroxide, let's say. Right? In this case, 32 plus 2 is equal to 34 grams. So consistently, when any reaction was run, the mass of all the products was equal to the masses of all the starting materials. So this is our law of conservation of mass. Now there's one more important observation that helped him to nail down the atomic theory. Notice that in this case we have 32 grams of oxygen per 4 grams of hydrogen. In other words, a ratio of 8. And in our lower reaction, we have a situation where 32 grams of oxygen are reacting with 2 grams of hydrogen for a ratio of about 16. And notice that those two ratios themselves are very simple whole number multiples of one another. In other words, you either can have a ratio of 8 or a ratio of 16, which is double that, but never in between. So Dalton noticed this and coined this the law of multiple proportions. And it's the combination of the law of conservation of mass and the law of multiple proportions that gave him an airtight argument for the existence of indivisible atoms that come together in these simple whole number ratios to create molecules. So Dalton's genius was to combine the laws of conservation of mass and multiple proportions to make an argument for the existence of atoms. It was the only possible explanation for what he saw. An argument so strong that it finally restored traction to the atomic theories of Democritus and Plato. Dalton himself said, "Matter, though divisible in an extreme degree, is nevertheless not infinitely divisible. That is, there must be some point beyond which we cannot go in the division of matter. I have chosen the word atom to signify these ultimate particles." But Dalton believed that he had reached the end of the story. In his mind, atoms were the ultimate particles of matter, and nothing smaller could exist. For his purposes, thinking of atoms as indestructible, undissectable pieces of matter worked. Now, we would have to wait another century before technology caught up with the atom, leading to the realization that the inner workings of this remarkable construct of nature depend on a complex but predictable combination of even smaller particles that we call subatomic particles. The first of these advances is one which most of us are familiar with. It has only been a decade or so since that large, heavy, nearly cube-shaped television set finally gave way to the slim, energy-sipping displays that adorn the walls of your favorite big box stores. But the technology on which these household devices of the late 20th century were based actually was devised much earlier. The cathode ray tube, or CRT as it is sometimes called, was actually developed at the end of the 19th century, and it played an important role in the advancement of human understanding of atoms. Thomson's cathode ray tube. It was a fairly simple evacuated glass tube. Now, this tube contained 2 discs. And those discs were each connected to one terminal of a battery, creating an electrical voltage across those 2 plates. The negatively charged plate would be called the cathode, and the positively charged plate would be called the anode. Now, when this apparatus is constructed, a beam of some sort can be observed traveling from the cathode to the anode. And Thomson used an anode with a small hole in the center, which allowed the beam to continue along the body of the tube. Now here, in this environment, he could study that beam. Unperturbed, of course, the beam was perfectly straight. But Thomson noted that when he placed charged plates at the top and the bottom of that tube, that the beam bent ever so slightly in the direction of the positive plate. Now, this told Thomson two important things about what was making up his so-called cathode ray. First, it had to be negatively charged because the positive plate attracted it. This prompted him to name these new particles electrons. Second, and maybe even more importantly, the extent to which the beam curved allowed him to estimate just how massive each electron in the beam must be, since larger particles would necessarily be deflected less by the charged plates. Now, using that cathode ray tube, J.J. Thomson was able to create isolated beams of pure electrons and measure their mass, velocity, and charge. His measurements, though, led him to a startling conclusion. The electrons in that beam were smaller than atoms. This led Thomson to propose the first ever structural model for an atom. More than 100 years after Dalton repopularized the concept of atoms, the first real attempt to explain their structure had finally been offered. Thomson postulated that atoms consisted of the small, negatively charged electrons he had observed embedded in a very low-density, positively charged spherical matrix, making up the rest of the atom's mass distributed throughout that sphere. A sketch of his model with electrons peppered into a positively charged sphere evokes images of raisins in a bowl of pudding, earning it the moniker of Thomson's plum pudding model. But this first attempt to explain atomic structure was short-lived, as less than 2 decades after Thomson proposed his plum pudding model, his own protege, Ernest Rutherford, conducted an experiment which was intended to build on Thomson's model, but instead disproved it outright. Rutherford is credited with the discovery of what are known as alpha particles. Alpha particles are a much larger charged particle, more than 1,000 times larger than electrons, and they're created during the radioactive decay of heavy elements like uranium. But Rutherford is not most famous for discovering these particles. He's most famous for what he did with them next. Rutherford was curious to know how these relatively large, energetic alpha particles would interact with atoms as they passed through a thin foil of atoms. So, he pointed a beam of alpha particles at a piece of gold foil, encircling the foil in a special fluorescent screen which would light up when struck by an alpha particle. Assuming that Thomson's model was correct, the alpha particles were expected to simply pass through the foil, being scattered only slightly, if at all. As the experiment progressed, Rutherford noted that the brightest spot was directly behind the gold foil, just as he expected. But Rutherford was stunned when he turned his attention to the other side of the screen in the direction of the source beam and saw that a few particles were deflected almost directly back toward the source. Clearly, Thomson's model could not be correct. If the mass of gold atoms was distributed across their entire volume, then there is no way that an alpha particle could possibly be reflected back towards its source by those atoms. They're simply not dense enough. Rutherford's results strongly indicated that atoms were made of mostly empty space, but with a highly concentrated nucleus containing almost all of the atom's mass in just a small fraction of the atom's total volume. This would explain why, on rare occasion, an alpha particle bounced back. Only an extremely dense point of matter, taking up a very small volume of the atom's total, could possibly withstand the impact of an alpha particle and cause it to ricochet backwards in its original direction. Rutherford's own words probably best describe this. He famously recounted of his own experiment. "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you." So there had to be an extraordinarily dense but vanishingly small point of mass at the center of atoms. Very dense to explain the ricocheting alpha particles, and vanishingly small to explain why just a handful of those ricochets took place during Rutherford's experiment. Rutherford realized then that atoms were mostly made of empty space, with that dense point of matter at their center. His model accounts for this and has been dubbed the Rutherford model. sometimes also called the nuclear model, because it's the first to acknowledge that most of an atom's mass resides in that small, dense nucleus at its center. So Rutherford had discovered that atoms consisted of dense, positively charged nuclei surrounded by very light, negatively charged electrons. But just how small is a nucleus really? Now recall that we've already learned just how small atoms are, having diameters of about 100 picometers. That's about 1/10 of a nanometer. Now, Rutherford's work eventually led to the discovery that the radius of a typical nucleus is only about 1/100,000th that of its electron cloud. That's 1 femtometer, 0.000001 nanometers. Now let's put that into perspective. That means that if an atom were 1 meter across, its nucleus would be the size of a dust mite. If that same atom were as wide as a football field, the nucleus would be just about a millimeter wide, the size of a grain of sand. And to get a nucleus the size of that football field, the atom would have to be the size of planet Earth. Now, if you were an electron with an orbit the size of Pluto, looking back at the nucleus, it would appear to you like this, just a speck in the distance about the size of our own sun. So Rutherford had determined that massive, positively charged particles were concentrated in the nucleus of the atom. Protons had been discovered. But there was one last bit of observation to account for. As research on radioactivity continued, there were some observations about atomic nuclei that weren't quite adding up in a very literal sense. Specifically, researchers had irradiated beryllium with alpha particles to produce a new kind of radiation, one that didn't bounce back off of the nuclei the way Rutherford's alpha particles did, but instead crashed into them with force, penetrating deep inside and knocking protons out of the target atoms that they struck. The final key to understanding these unusual observations came in 1932, when James Chadwick, formerly a student of one of Rutherford's own assistants, completed the inventory of subatomic particles. Chadwick reasoned that this newly discovered radiation was able to penetrate other atomic nuclei better because it was uncharged, whereas alpha particles used by Rutherford carried positive charge and were repelled by the positive nuclei of the atoms they struck. This explains their tendency to ricochet and bounce back. But these new particles, though massive, were able to get deep inside the nuclei they struck without bouncing back. They had to be uncharged. The lack of an electrostatic repulsion allowed these new particles to strike those nuclei with great force, a force that Chadwick used to estimate their mass. And he dubbed these particles neutrons. And quite interestingly, he discovered that they were just a fraction of a percent larger than protons themselves. Because protons and neutrons are so similar in mass and so much larger than electrons, they contribute nearly all of the mass to an atom. Chemists use a unit of mass called the atomic mass unit, or AMU, to compare masses of atoms to one another. And protons and neutrons themselves each weigh just about 1 atomic mass unit. So this very convenient unit of measure leads to a nice round number for communicating the mass of an individual atom. So by 1932, the combined thought of ancient Greeks, Dalton, Thomson, Rutherford, and Chadwick, and of course many, many others, had led us to an understanding of an atomic structure that looks something like what you see today in popular depictions of the atom. Let's start with the simplest atom of all, an atom of the element hydrogen. Now, all atoms consist of that dense central core of matter called the nucleus, and in that nucleus we always find one or more protons, and in the case of hydrogen we have just one. Around that dense positively charged core are electrons, and again in this case we have just one electron to balance the positive charge from the proton in the nucleus. This is a complete hydrogen atom, complete with a proton at the center and an electron orbiting. Now, we sometimes refer to this version of hydrogen as protium because its nucleus contains just a single proton. Now remember, don't let this scale fool you here. I have drastically increased the size of that nucleus to make it easier to see. If the atom were really this size, the nucleus would actually be about the size of a grain of sand. But we need to see what's going on here, so I've increased it. Now, it's the proton count in the nucleus that gives an element its identity. So I can add a neutron to my construct here, and I still have hydrogen. But now my hydrogen atom is twice its original mass. So we call this type of hydrogen, one in which a neutron is also present, deuterium. And this is more massive than protium. I can increase the mass of deuterium yet again by adding another neutron to it to get what we call tritium, another form of hydrogen. And this one is 3 times more massive than the hydrogen itself, the protium. So all 3 of these atoms are hydrogen, but clearly they are different from one another by way of their masses. When we have a situation like this, we call these groups of atoms isotopes of one another. So protium, deuterium, and tritium are all isotopes of hydrogen, and their chemical properties will be very, very similar, even if their atomic masses are not. We sometimes distinguish them by writing their elemental symbols with a superscripted number to indicate the mass of the isotope itself. In this case, hydrogen 1 for protium, hydrogen 2 for deuterium, and hydrogen 3 for tritium. Now let's focus in on that tritium, and let's put another proton into the nucleus and change the identity of our atom. Now that I've added another proton to the nucleus, I have to add an electron to its cloud as well to balance out the charge. We now have a new element because the number of protons in the nucleus has changed. We've taken our first step across the periodic table to create an atom of helium-4. Add another proton and an electron to balance it out. We have what would be called lithium-5. But lithium is most often found with 2 additional neutrons as well, making it lithium-7. This is the most common isotope of lithium. Add another proton, and another neutron, and another electron, we get beryllium-9, and so on. So we can estimate the atomic mass of an elemental isotope simply by adding up the number of protons and neutrons in the particular isotope. For example, a carbon atom will always have 6 protons. So if I want to talk specifically about a carbon atom with 6 neutrons in its nucleus as well, I would write its elemental symbol like this, the notation for carbon-12, its most stable isotope. If instead I have a carbon with 7 neutrons, its mass is 6 plus 7, or 13 for carbon-13. And again, I can add 1 more neutron to get 8. I now have a total of 14 particles in the nucleus for a mass of 14. This is the famous carbon-14 isotope used to radiometrically date archaeological finds. This same notation can be used for all elements. Take a look at uranium, for example. All neutral uranium atoms will have 92 protons and 92 electrons to balance that charge. Add 143 neutrons and you have uranium-235, a relatively rare isotope of uranium, which is highly unstable and can shatter in an instant, making it useful for the construction of nuclear weapons. Instead, add just 3 more neutrons and you get the isotope uranium-238, an isotope which radioactively decays, but it does so over billions of years, giving us a clock with which to measure processes as old as the Earth itself. There are many elements that exist in nature as 2 or more isotopes. In fact, most of them do. And when this is the case, the periodic table will report an average mass for a given element in nature. For example, you may notice that chlorine atoms exist in nature as 2 different isotopes, chlorine-35, which is about 75.8% abundant, and chlorine-37, which is about 24.2% abundant in nature. A quick look at the periodic table shows us that if we consider a large collection of chlorine atoms, knowing the relative populations and masses of the isotopes that make it up, the average mass of a chlorine atom is 35.45 atomic mass units, just as the table reports. This doesn't mean that there's a fraction of a particle in the nucleus. It simply means that there are multiple isotopes that are abundant in nature. So far, we've confined our discussion of atoms to situations in which the number of protons and the number of electrons are exactly the same. That's convenient because their opposing charges balance one another out, resulting in an overall neutral atom. But what happens when they're not balanced? As you might expect, when the number of protons and electrons are out of balance, we create a species that carries a net overall charge. These charged species can have properties that are drastically different than their corresponding neutral atoms. Chemists call these charged atoms ions. And in general, if there are excess electrons, we get a negatively charged ion called an anion. If there is instead an excess of protons, we get a positively charged ion, which we call a cation. For an example, let's take a look at the element fluorine. With 9 protons and 9 electrons, fluorine looks something like this. But if we add 1 extra electron to it, we get what's known as a fluoride ion, an additive sometimes included in toothpaste or drinking water to help strengthen your teeth. We can create an ion with an even greater charge by adding even more electrons. Consider oxygen, for example. If we add 2 electrons to oxygen, we get what is commonly called an oxide ion. This is the form of oxygen that we find in rusted metal, for example. Let's take a look at sodium now. With 11 protons and electrons, we can remove an electron from sodium, creating a positively charged sodium ion. That charged sodium ion, not the neutral sodium atom, is that pesky form of sodium that your doctor keeps telling you to cut down on in your diet. And just like anions, cations can carry greater charge when the discrepancy between electrons and protons is greater. For example, magnesium would have 12 electrons as a neutral atom, but when found in rock-forming minerals like limestone, those magnesium atoms are missing 2 electrons, forming a cation with a +2 charge. So let's take a moment now and review what we have discussed so far. We started out considering how nature uses combinations of smaller, simpler components to create tremendous variety in a wide range of scales, from galaxies to biological systems. We saw how atoms are not so different, having only 3 components called subatomic particles: protons, neutrons, and electrons. We saw how protons and neutrons reside at the center of the atom in its nucleus, giving the atom most of its mass, and how electrons orbit that nucleus, balancing out the positive charge at the atom's center. Then we talked about the ancient Greek philosophers and their debate over the most basic components of matter, which led to the coining of the term atom, meaning indivisible. We saw how this term falls short in describing atoms as we know them today, but its deep history in the discussion has led us to keep its namesake for the building blocks of the elements. Next, we took a look at how the work of John Dalton reignited the discussion about atomic theory 2,000 years after it was first proposed, and how he did this by considering the law of conservation of mass and the law of multiple proportions. We then saw how the work of J.J. Thomson led to the discovery of the electron and the plum pudding model of the atom, and how his protege, Ernest Rutherford, bounced alpha particle radiation off of gold foil, coming to the conclusion that atoms were in fact comprised of a dense nucleus containing protons. And 2 generations later, we saw how James Chadwick discovered the neutron by investigating this unusual type of radiation that didn't bounce off of the atoms it hit, but instead penetrated them. Once we had our inventory of subatomic particles, we took a deeper look at the structure of the atom. We saw how the number of protons gives an atom its identity, and how we refer to the number of protons in a given element as its atomic number. We then saw how the number of neutrons can affect the mass of an atom, generating what are called isotopes. We saw how the number of protons and neutrons together is referred to as an isotope's atomic mass. And finally, we saw that by adding or removing electrons in an atom's cloud, we can impart them with an overall charge, creating positively charged cations or negatively charged anions. But what neither Thomson nor Rutherford could possibly have known in their day is that the cloud of electrons around a nucleus is far from uniform. It actually contains a very complex system of electron orbits, And the position of electrons within the cloud of an atom, or ion, is one of the most significant driving factors in how these elements behave. Next time, we're going to dive deeper into this structure and investigate the electronic structure of the atom.